efficient diffusion language models. Nowadays, we know diffusion language model has a very promising capabilities to generate the text, but here's a code problem about the efficiency of different language model. So there was some approximation error during the first step decoding of the DLM. So in this work, I will talk about the accelerating different language models via self-trajectory distillation. Like in this framework, we don't need the ground truth level. We use the model itself to prove its performance in the first step decoding tasks. So let's move on. Okay, here's the quick roadmap. First part, I will introduce some background of different language model, including the masked diffusion language model, MDIM, which is a popular framework nowadays to have some performance even better than autoregressive or very competitive to autoregressive model, and will be widely used in practical problem. And next, I want to talk about the challenges of the field-step decoding of different language model. And next part, I want to introduce in our method T3D. And in this method, we use the trajectory self-distillation and the data. And we also use a DDO objective to do the training. And this objective actually a reverse chaos star objective and can help the model to learn the field step via a mode thinking objective. And next, I want to show some experiments on our method. And finally, I will provide some theory justification to support the correctness of the T3D. And next, I will talk some future directions of this work that we can do. Okay. Okay. So firstly, I want to introduce the difference between autoregressive model and diffusion language model, especially for masked diffusion language model. And autoregressive model, AI model, like ChatGPT, Gemini, and has been widely used and shows a good performance in problems. And actually, this kind of model just generates text sequentially, token by token. You can see this figure A. The left one, the figure A shows the autoregressive generation, like giving a prompt, and we predict the next token, token by token from left to right. And every time I just predict the next one token. And the key limitation of this framework is I can only do prediction for just one token in every step. So this limits the decoding efficiency of natural language generation. Okay, but masked diffusion language model give our different diagram. Like MDM just generates text by iteratively refining masked tokens in parallel. Like the figure B shows our diffusion process generation given a prompt which is in blue box, and also I have to give a response, but this response is all constructed by the mask tokens. And like I start from the masked sequence and I do the diffusion step. Sorry, I do the diffusion step iteratively, and every step I just predict some mask token into real token. And this is done in parallel. So that means in every step, I can decode more tokens. And also the decoding token is not left to right. It's based on the confidence of the model to the decoding token. So the MDM has a potential to do the faster and more efficient generation. So we can call this MDM as a mask predictor because every time it just predicts tokens from the mask. Okay, this is a key difference between the MDM and autoregressive model. Okay, let's move on. And here, I want to show an overview of the MDIM. This figure comes from the very popular work LADA. And you can see figure A. This is the pre-training framework of MDIM. Like I have a clean sequence, and I just corrupt this sequence using a mask token, the mask token, and I have to sample a mask ratio T from a uniform distribution, and I use this T to as a probability to corrupt the tokens in the sequence, and I do this corruption independently, so we can get a corrupted sequence which consisted of clean tokens and mask tokens, and this is actually the training samples, especially the inputs for the MDIM, and I just input this corrupted sequence to our MDIM, and I ask the model to predict the real token from the mask token, and I can compute the loss function and like a cross entropy, and I can optimize this process, and this is the pre-training framework. And figure B shows the supervised fine-tuning process. This is similar to pre-training, but here I just fix the prompt unchanged. I only do the corruption in the response part, and I do the mask predictor and compute the loss. And the figure C shows the inference process. Like I have trained the model to do the diffusion process. Now I have a prompt, and I start from a prompt and concatenated with a mask response, and I do the diffusion step iteratively every time I predict some tokens again and again. And after all these intermediate steps, I can get a clean token. And this is actually the reverse process of diffusion. So now we know how to do the inference in the MDIM framework. All right. And so diffusion language models have some properties maybe can help us to do the text generation. Like DLM can start from noisy or mask and iteratively refine it, and it can predict multiple tokens in parallel. And MDIM use full bidirectional context and array step. And here's the figure shows the timeline of diffusion language models. We can see we have the first models in 2021, D3 PM, and from 2021 to now, we have so many different diffusion language models. And why is so many companies, so many research institutions are so interested in diffusion language models? I just summarize some points, like because diffusion language model can do refinement, but without long context overhead and less cascading error than autoregressive decoding. And diffusion language model also maybe can do better reasoning because it can do the correction for the previous decoded tokens, and maybe it can help us to get a better reasoning path. But here's a core problem of the diffusion language model about the efficiency. That is the challenges of few-step decoding. Here, I just did a very simple experiment. I use a powerful and popular diffusion language model called STAR, and this is a 4B LLM, and I just fix the decoding block is 4, and I define the tokens per step called TPS. This is just measures the throughput of the model, like how many tokens I can decode per step. If I set TPS is 1, and that means I need every step I just decode 1 token. And if I set block size is 4, that means I need 4 steps to decode this block. And if I set decoding step is 1, that means I ask the model to predict all 4 tokens in this block simultaneously. So this will be a huge challenge for current diffusion language model. You can see the performance degradation of this model. and I increase the TPS. That means I decrease the decoding step, and the performance just drops sharply. And you can see when TPS is 4, or I can say when decoding step is 4, and you can see the model can get almost 70% accuracy on mass 500. But when I ask the model decode this block just using one step, and it just drops to only almost a 10% accuracy. So this indicates that aggressive parallel token prediction harms the generation quality of DRM. And so why is field step false? Maybe some train test mismatch, maybe factorization error, and many reasons. But we have to solve this problem. So why solving field step matters? I think because if we can decode in lower, because if we can decode in field step, we can have lower latency, lower computer cost, and higher throughput. It is very important in real life problem related to the deployment of the diffusion language models. So in this work, we just analyze the reason and we address this issue. Okay. And here is an analysis to why the parallel decoding is not good for diffusion language model. We have to recall the mean field assumption. This assumption was introduced by most of previous diffusion language model work. That this assumption, like I just can factorize the tokens in the status like this. And this assumption actually means we just assume all tokens are independent. Or we can say if we can predict all tokens in the same sentence, they have to be independent to each other. But actually, obviously, this is not correct in natural language generation because we know there should be high correlation between tokens in a sentence. If one token just show up, then it will affect the other probability of this of tokens in this sentence. So this assumption will introduce huge approximation error in field step generation. We have to address this issue. So the problem becomes, can we reduce mean field approximation error on the tighter step budgets for DRMs? We have to figure out this problem. Okay, actually, some previous works explored this mean field error. Like already, this work use a rectified flow intuition, like in the continuous diffusion model. But unfortunately, it's not compatible with the MDLM framework. We can prove this point. This is not compatible. And another work, EDLM, energy-based diffusion language models. This method just trained an extra model to modify the distribution of DRM in the field step generation. But it needs MCMC sampling, and it will introduce higher cost, higher computation cost. So here we just introduce our method T3D, and this method is a training framework for the efficient diffusion language models, and T3D actually uses the model thinking objective to do training, and this point is very important in field step generation of diffusion models. Previous works on image domains have proved this point, the model thinking objective. And T3D allows aggressive field step generation, and it can preserve the diffusion capabilities. And the most important point is it's totally label free because this is the self-distillation or self-evolve framework. We don't need to introduce the ground truth label. We don't need to more powerful model to teach this model do this. We just use the model itself to teach itself. Okay. Okay. Here's the overview of our framework. We can see the figure A is a teacher full trajectory. That means we have a pre-trained diffusion language model, and we just define the teacher and the diffusion language model can do generation token by token. Like for teacher model, every step I just decode one token, and I just do this generation for all the data set, and I can collect the trajectory generated by the model itself. And here are the assumptions that we think the trajectory generated like this will be better than the generation in field step. So we use this as our positive samples to as a guidance for the student model learning. Okay, and the figure B shows the how do we do this training, and we can see we have a reference model here, and this reference model is initialized from student model P theta, and we use this reference model to generate negative training samples. Like every step, I just use this reference model to generate a bad training samples as a contrastive learning style objective. And every time I just ask the reference model do the one-step prediction. So the data quality generated by this reference model will be very low. And so I can collect the positive samples generated by the teacher and the negative samples generated by the reference model. And I have a data pair, a pair of positive and negative samples. Then I use direct discriminative optimization, which is used to perform model thinking, trajectory matching, and I just want to let the student model P theta learn the distribution matching of the teacher model. So this is actually a policy method and discriminative optimization method. So the figure C just shows the field step decoding. We can say after the training, the student can decode using field different step. It can just skip some intermediate steps during its decoding and improve the efficiency. And in this framework, we don't need to more powerful teacher model. So totally self-distillation and level free. All right, here I'm going to show some details of our framework. T3D, the first part of T3D is trajectory self-distillation, like how we collect the positive samples. This is a very important part in our work, and it's the key difference between our work framework with the naive supervisor fine tuning. And suppose we have a pre-trained teacher model, and this teacher model always do full-step diffusion generation. Like every step, it just decode one token. And so now we train a few step student model P theta, and we can sample from teacher model to collect the real trajectory generated by the model from x0 to xt. And x0 is the clean token, clean sequence, and xt is a fully masked sequences. And we can draw a clean noisy pair from this trajectory x0 and xt. So this is our positive samples, and our target is learning the joint distribution of this pair generated by the teacher. And here's the takeaway. This is a policy training. That means we just train on what to execute. because we generate data from the model itself. So that can remove the distribution mismatch. And this method, there's no architecture change required and totally level free. The next part is DDO style objective training. So direct discriminative optimization is a GAN-inspired objective. But instead of training a discriminator in DDO, we can implicitly parameterize the discriminator by the log ratio of your model p theta and the reference model. And this is also a reverse chaos objective. Like here, the left one is a K objective. We sample from teacher, we sample xt from teacher model, and given xt, we sample x0 from teacher model. And this loss function means we want to maximize the log likelihood of the student model. But the right one is the reverse K objective. We can sample xt from teacher, but for the x0, we sample a positive one from teacher and we sample a negative one from the reference model. So this is the discriminative optimization. And actually in our work, we just adopt the reverse K objective. And the takeaway is typically we think forward KL means mode covering, and first step diffusion needs confident mode thinking. Yeah, this point has been proved in previous image domain first step diffusion. And the reverse KL can encourage the commitment of the mode thinking. That's why we adopt the reverse KL objective. Okay, the last part of the T3D is the path consistent regularization. We design a path consistency regularization, which is actually a KL objective. So in our framework, we just combine the KL and the reverse KL objective together to train our method. And actually, we do some modification because we have an assumption that if the token was decoded earlier, then the token is more important for the overall stability. So in this loss, we have a weight Wi, and is controlled by the pi. Pi is the decoding order of the token I. So intuitively, we just pay more attention to early decoded tokens. Early decoded token will have a larger weights in this loss function. We think this can improve the overall decoding stability. And this is the overview of our training algorithm, the teacher model P5, and we initialize the student model P theta from teacher, and we can do sample trajectory pairs from the teacher, then get the x0, xt, and now we do training. We set the reference model from p theta and compute the DDO loss, compute the path consistent loss, and we combine them together and do the training. This is the whole framework, a very simple training loop. Okay, to experiments, we design several experiments to show the correctness of our method. First one is field step decoding. Here we just set a different block size, different decoding step, and we can see the original model. When we do the field step decoding, the performance is not good. Like here, only 5% accuracy on mass 500 cannot be used. But for T3D, we can see we have T3D consistently achieves the best or near best performance among all baselines. That can improve the performance of the diffusion LLM in field step decoding. So yes. And next part is the experiment on full step decoding preserving. Somebody might ask, okay, now you train the model to do the faster generation, do the few step generation. But if I want to do the full step diffusion, like I want to get better results, I want to have a better performance. So I want the model can do the diffusion carefully. So after the training, can you still do that? So this experiment, we just study the potential diffusion behavior for gating after the few step distillation. And actually, we just revert distilled model back to full step diffusion process and evaluate the performance. We can see there's almost no any performance loss in our T3D method. You can see the baseline D parallel to almost forget all the diffusion properties. So that means D3D can generalize to full diffusion performance and enables few step generation without sacrificing full diffusion performance. Yeah. And the last experiment is efficiency on dynamic decoding. Like in real application, in most of cases, we will use dynamic decoding. That means we can set a threshold, and every time I just decode all tokens, which their confidence is larger than this threshold, which means confidence-based adaptive decoding. So a T3D is trained for static field step, but we test it on real-world inference setting using dynamic decoding. We can see the results. T3D has a better accuracy and reduces the average decoding steps and achieves lower latency and delivers higher throughput. That means T3D can generalize beyond static decoding. It can be used in practical applications and has a potential to be deployed directly. Okay. Okay, the final part is some theory justification to support the correctness of T3D. And the fourth part is on policy optimum. Like we can define the on policy risk for this distillation, and we can show the T3D is optimal for this risk. Like the optimal solution for T3D is also the optimal solution for this risk. That's because we just train the model on itself generation trace. So this student is trained on the same intermediate state distribution encountered and inference time. Actually, this self-distillation ensures on policy alignment with the teacher. It can avoid the mismatch caused by random masking training. And the next part is T3D can reduce mean field factorization error. Like I said, why the diffusion model falls in field step? Because it has a very high factorization error. But we can show T3D can induce this, can induce lower this factorization error. We defined conditional total correlation, which is a KL divergence between the probability of sequence and the factorization of the tokens. And we can prove the T3D can get a lower conditional total correlation. So that's why T3D enables the fewer step decoding of different language models. All right. In summary, we just do two things. The first one is distribution alignment. We train on what you execute. We use self-distillation. That means we have a distribution alignment. and this can help us to get optimal policy optimization. And another one is objective alignment. We use a reverse chaos style training objective, and we can induce lower factorization error. That's why we can optimize the model to do the first step decoding. For future directions, we can try maybe we can train this model on task or domain-specific decision. We can scale up the dataset. We can use larger or better datasets. For now, we just use a very basic dataset consists of only 8,000 samples. It's very small. So later, maybe we can just scale up the dataset. We can scale up the model, and even we can just try to incorporate the explicit reinforcement learning into this framework to improve the performance. So yeah, we have a lot of works to do in the future. Okay, here's some references, and yes, thank you. I'd happy to take any questions.
Okay, you can speak first. Yeah.
Can I go ahead?
Yeah, please.
Yeah, sure. So yeah, I'm not so familiar with the. But first of all, yeah, thanks for the great presentations. And honestly, I'm not so familiar with the diffusion models because I mostly come from the natural language processing field. And I wonder, if you go back to the loss function,